and welcome to Module 9. In this module, we'll learn about the relationship amongst all the types of stars in the universe. Distances to nearby stars are determined by stellar parallax. The motion of nearby stars among the background of more distant stars, due to the Earth's motion around the Sun, is called stellar parallax. Remember what the equation for parallax is. D is equal to 1 over P, where D is the distance to the star in parsecs, and P is the parallax angle of that star in arc seconds. The first stellar parallax measurement was made in 1838 by Wilhelm Bessel, a German astronomer and mathematician. For a review on stellar parallax, please revisit the Module 2 presentation. If a parallax angle is smaller than 0.01 arc seconds, then it cannot be measured with an Earth-based telescope. So in 1989, we launched a satellite that was able to measure the distance of over 2.5 million stars up to 500 light years away. The image on this slide is the M5 star region.
Notice all the pretty colored stars. Why are there blue stars, red stars, or yellow stars? Why do some look bigger than others? Why do some look brighter than others? That is our topic here in Module 9, how we're able to understand luminosity and energy across the universe. The M5 region is a globular star cluster of over 100,000 stars, bound by gravity and packed into a region around 165 light years in diameter. It lies some 25,000 light years distant from us, and this stunning Hubble close-up view spans about 20 light years across, near the center of the central region of M5.
Apparent magnitude measures the brightness of stars as seen from Earth. We distinguish between apparent magnitude and absolute magnitude. So the brightness of stars, without regard to their distances, is called apparent magnitude.
So that is just dandy. Now we have centuries of volumes of books comparing the luminosity of stars as we see them from Earth. The only problem with apparent magnitudes are they tell us absolutely nothing about the actual luminosity and energy output from stars. Obviously, if you move our bright yellow sun to, say, 5 billion light years from Earth, it's going to appear just a little dimmer in the night sky. In fact, you won't even be able to see it, because it's too far away to be seen with the unaided naked eye. However, after the invention of the telescope in 1608, we began not only to see more stars in the night sky, but when viewed in the telescope, many of these stars were now brighter to the naked eye than the brightest naked eye stars the Greeks had labeled as M+1. So the invention of the telescope itself is just our problem. Now that we see brighter stars in the night sky, how do we number them? How are we going to assign apparent brightness numbers to all these millions of new stars we were seeing through the telescope? If M+1 are the brightest and M+6 are the dimmest stars we can see, what's left? M+7? Well, no, that would mean an even dimmer star than M+6. And while we're thinking about it, just what are we going to do with all these volumes of books compiled over the centuries loaded with all those apparent brightness naked eye values? I know. If M+1 is the brightest visible naked eye star, let's label every star we see in a telescope that is brighter than an M+1 with negative numbers. Bada bing, bada boom, problem solved. An M-3 star is brighter than an M+3 star. An M-6 star is brighter than an M+6 star. Seriously, I'm not making this up. And while we're at it, we'll even keep the same integer scale the Greeks invented. So a star that's twice as bright as an M1 star, we will forever call an M-1 star. Yup. An M-1 star is twice as bright as an M+1 star. So clearly, an M-2 star is twice as bright as an M-1 star. Thank the telescope for negative brightness numbers. Simply, the rule of apparent magnitude is the more negative a sky's object, little m value, the brighter it appears to us here on Earth.
Unfortunately, it gets uglier. The brightest stars and some other objects in the sky are actually brighter than the original apparent magnitude stars. In this image, you see several stars in and around the constellation Orion, labeled with their names and apparent magnitudes.
You see, safe at the bottom is a +2, and never mind.
Recall that stars with negative apparent magnitudes appear brighter than stars with positive apparent magnitudes. So the more negative, the brighter. Since stars are all at different distances from us, apparent magnitudes do not directly reveal any fundamental stellar properties. Only absolute magnitudes can reveal fundamental brightness differences between stars. Absolute magnitudes and luminosities do not depend on distance. Although absolute magnitude gives us comparisons between the energy outputs of stars, we also need to know the total energy they release. The total amount of electromagnetic power, which is energy emitted each second, is called a star's luminosity. Professor Quasar, what is L circled dot?
Ah, L circled dot. Well, to be honest, astronomers love to obfuscate. Look that one up, students, and often. You first met with this lunacy with the apparent magnitude scale, where the brightest stars we see are denoted with negative numbers. So again, an M-3 star is brighter than an M+3 star. Thus, when astronomers realized that they would have to write the word luminosity, and that big giant number 3.83 times 10 to the 26 watts, every time they wanted to talk about the sun's energy output, they had heart palpitations, and a solution was needed. They developed a cryptic shorthand that is so obscure that even the dumbest of eggheads could love it. Astronomers agreed that the yardstick they would use to compare the luminosity of all stars in the universe would be based on our sun's luminosity output, which is 3.83 times 10 to the 26 watts per second. Therefore, one circled dot, read as one stellar luminosity, equals 3.83 times 10 to the 26 watts per second. And since we all know we are talking about our sun when we say one L circled dot, why even write the number 1? That's just a waste of time. L circled dot stands for solar luminosity intensity, and solar luminosity intensity is 3.83 times 10 to the 26 watts per second.
Combining all of this data allowed early 20th century astrophysicists to discover the surface temperature range of stars throughout the universe. This led to the Kelvin temperature scale that astronomers use today.
Alright, so we'll try and explain apparent magnitude versus absolute magnitude. Apparent magnitude, the ways the stars appear to us in the night sky. The absolute magnitude scale is the range of the luminosity or intensity of all stars in the universe. And this scale runs from M-10 to M+17, the dimmest. Remember, the bigger the number, the dimmer the star. The brightest stars in the universe have a luminosity of 10 to the 6 L circled dot. And remember, we learned that L circled dot is the shorthand symbol for the amount of the sun's luminosity outputted per second. which is 3.83 times 10 to the 26 watts per second, a tremendous amount of output. So what the absolute magnitude scale tells us is the brightest stars in the universe have 1,000,000 times the luminosity of our sun. We read it as 10 to the 6 solar luminosities, or 1,000,000 times the luminosity of our sun. At 10 minus 5 solar luminosities, that means that these dimmest stars in the universe have a brightness of 1/100,000th of the output of our sun per second, which again, the output of our sun per second, 3.83 times 10 to the 26 watts, which we simply shorthand as L circle 0, and we refer to it as the sun's luminosity, or 1 L circle 0. The other symbols we will find, we deal with M circle 0. This stands for the mass of the sun. How massive is the sun? It's 1. Okay? There's a radius to the sun. How big's the radius? Who cares? Okay, the answer is 1. Because we compare the entire universe energy output based on the energy output of our sun, which is at 1, which is the departing point for the Hertzsprung-Russell diagrams. Okay, so here we go. So here's our sun. All right, smiley face. Here's us. And here is a mythical line I just drew in space at a distance of 10 parsecs, or 32.6 light years. Of course, there's lots of stars out here beyond that distance, and there are stars closer than that, like our sun. So the solution of how we can move all the stars in the universe relies on an important principle of radiation discovered by astrophysics, which we call the inverse square law, which we'll deal with over the next couple of slides. But the idea is, if we could take deep space line stars and move them to this distance, that might be that big, and our sun moved to this distance might be this big, and some other stars might be that big, and if they're all on a straight line, we could compare their luminosity against one another, and we would have an absolute magnitude value scale for the energy emission of all stars in the universe. This is how we move stars using the inverse square law, which we will cover very shortly. Okay, thank you, and now we'll move on. You are looking at deep space. I am a deep space star. I have very little luminosity because I'm so far away. But don't think I'm not as powerful as your sun. Watch this. As I get close to you, I get more luminous, I'm burning your eyeballs out. Is that because I have more luminosity now than I have when I am back here at your eyeball? The answer is no. What you're seeing is the change of luminosity with distance, which follows the inverse square law. I seem to be a dim star, but up here I'm stronger than your sun. Woo! Inverse square law. Dimming with distance. Bright distance, I go the other way. Whoa, a tiny, tiny little spot. Inverse square law of light, thank you.
So to understand the relationship between absolute magnitude and apparent magnitude, we need to know how brightness of an object changes with distance.
And this dimming of light with distance follows the mathematical formula called the inverse square law.
Apparent brightness decreases inversely with the square of distance between the source and the observer. The inverse square law, I, is proportional to 1 divided by d squared, where I is equal to the luminosity or intensity of brightness, and d is equal to distance in any units you choose, miles, kilometers, light years, etc.
In this slide, take a look at the distance d1. That can be, again, in any units you choose. Distance from the star is 1. Notice when you double that distance to where d equals 2, the amount of intensity of light that spreads out into the universe diminishes according to the inverse square law, 1 over d squared. So you get 4 squares of less brightness. At distance 3, 1 over d squared, 1 over 3 equals 9 squares, each of which has less and less energy per square. This is the meaning of the dimming of light with distance. Example 1. Take 2 identical stars, one twice as far away as the other. The farther one's brightness falls off, according to the formula, 1/2 squared, which is equal 1/4 the brightness of its closer twin by the time the starlight gets to us. Example 2. The sun emits 3.83 times 10 to the 26 watts per second of power, compared to 100 watts for a bright light bulb. The sun's power is spread over a wider and wider area as it travels through space. When it passes Mercury, sunlight provides 9,140 watts on every square meter of space. That same energy has spread out so much that by the time it passes us at 1 AU from the sun, it provides only 1,370 watts per square meter of space.
Hey, Professor Quasar, that sounds a little too astrophysics-like for me. Can you give me an Earth-based example to explain this critically important law that the dimming of light with distance follows a mathematical formula, the inverse square law?
Absolutely. Let's look at it using our car headlights as representing 2 stars emitting light in the night sky. Each headlight gives off a fixed amount of light, its luminosity. Question, Nova. If you turn on your headlights right now and I walk to New York City, do your headlights get less bright because I am now 2,000 miles away from them?
No, of course not. They have the same brightness. You can't see them because you're 2,000 miles away.
Really? Is 2,000 miles the problem? We see the light from stars that are hundreds of millions of miles away. Why?
Okay, I get it. Each source of light has an intrinsic brightness, and how far away a star is has nothing to do with its own internal energy output. What the distance from a light source does is dim the amount of light passing out into space, and this dimming of intensity with distance follows the inverse square law.
Correct!
Now back to the analysis of absolute versus apparent magnitude. As noted at the beginning of this section, absolute magnitude is the brightness each star would have at a distance of 10 parsecs. Now remember that 1 parsec is equal to 3.26 light years by definition.
And now we'll look at the surface temperatures of stars, following up on spectroscopy from section Unit 2.
There are 7 main types of stellar spectra based on surface temperature, and it is called the O, B, A, F, G, K, M sequence. This sequence is most easily remembered with the mnemonic device, "Oh be a fine girl, kiss me," or "Oh be a fine guy, kiss me."
So we have learned that the hottest stars in the universe range up to 50,000 degrees Kelvin, and we classify them as O-type. And the coolest are 3,000 degrees Kelvin, and we call them the M-type. Our sun is 5,800 degrees Kelvin, and therefore it is not an O or an M-class star, but one of the other star types.
The OBAFGKM stellar sequence is further divided into 10 temperature subranges, indicated by adding an integer from 0, which is the hottest, through 9, the coolest. Thus, an A8 star is hotter than an A9 star, which is hotter than an F0 star, which is hotter than an F1 star, and so on. But moving beyond that, the next logical question, to people like Professor Quasar anyhow, was what would we learn if we graphed stellar luminosity, or the equivalent absolute magnitude of stars, against the surface temperatures of the 7 spectral types O, B, A, F, G, K, M. This work was begun by astronomers Hertzsprung and Russell. The result yielded one of the most important astronomical tools of the 20th century. Graphing absolute magnitude versus surface temperature reveals a pattern. It shows that stars do not have random surface temperatures and L-circle dot. The two factors are related, revealing stars fall into a few basic categories. These graphs are known as Hertzsprung-Russell diagrams, or HR diagrams.
This is an HR diagram on a white background. I think black background is much more easily understood, and that's what we're going to switch to.
The band of stars stretching from top left to bottom right, with the red curve line, is called the main sequence. Each star on this band is called the main sequence star. Remember, the main sequence is defined by the fusion of hydrogen and helium into a star's core. Just over 91% of the stars surrounding the solar system fall into this category. Note that our Sun is on the HR diagram. It falls in the yellow surface temperature region and is also a main sequence star.
It's a main sequence star because it's performing hydrogen-helium fusion in its core, the definition for a main sequence star.
The Hertzsprung-Russell diagram, the most important thing to understand right away is that this is an abstract construction that compares the luminosity of all stars in the universe versus their surface temperatures. It's an abstract construction. This red line of stars does not exist in space. The red line represents what we call main sequence stars. Notice here's our Sun. Main sequence stars are stars that are still performing hydrogen-helium fusion in their cores. Over 91% of all the stars in our vicinity are main sequence stars, hydrogen-helium fusing thermonuclear devices. The other stars, such as these up here, which are the giants, and these down here, which are the dwarfs, are no longer performing hydrogen-helium fusion in their cores. So there is no line in space. And of course, there's millions of more stars in space. This is just an abstract representation. But look, luminosity of stars, remember we're basing luminosity in the universe on the Sun. So if we read over 1, you see that our Sun has the luminosity of 1. Vega would, at 10 to the 2, means it has 100 times the luminosity of our Sun, and is also a main sequence star because it is performing hydrogen-helium fusion in its core. The coloring also tells us the surface temperature. Vega is a white-hot star of A class of nearly 20,000 degrees temperature. The Sun is a G-class star of a temperature of roughly 5,800 degrees Kelvin on its surface. So this allows us to see that Betelgeuse, if we read across, is 10 to the 4th power luminosity of our Sun. In other words, 10,000 times the luminosity of our Sun. Right. On this side, we see the absolute magnitude scale compared to the luminosity scale. The surface temperatures run across the top, and the spectral types are represented at the bottom. We will see a practical application as we move on, but the function of the HR diagram is to let us understand that it shows all stars in the universe. Main sequence stars, stars that are performing hydrogen-helium fusion in their cores. star that's to the left of the main sequence is a dwarf, and any star that's to the right of the main sequence is a giant, as we will see as we examine the HR diagram. So I think we can start with that. Thank you.
An HR diagram also shows all other star types, like giants. Giants are to the right of the 0H main sequence stars. The star Pollux is an example.
So whenever you see a red star in the night sky, you can be assured that it is a giant because it's a cooler object than our sun.
Giants are 10 to 100 times the radius of the sun, with surface temperatures between 2,000 degrees and 20,000 degrees Kelvin.
Notice at the bottom, we even classify giants as giants and supergiants. And supergiants have a radius of over 1,000 times the radius of our sun, which is 1. But remember, the sun is so large in radius, 1,400,000 Earths would fit in it.
An HR diagram will also show you the dwarf stars.
Dwarf stars are the burnout remains of main sequence and giant stars. And at the bottom, I make note of the class of brown dwarfs, only because of the concept of solar mass. Notice brown dwarf stars have a mass of 8/100ths of the sun's mass. And this makes their temperature too low to initiate hydrogen fusion. And so they